Okay, this is session 7, sections 15 and 16. My name is still Ryan. What is due? Project 2 is due on Sunday, and on Wednesday, sections 15, 16, a quiz, and a discussion is also due. So let's get into the content. Section 15, we're going to start talking about normal distribution. Normal distribution, well, let's first talk about histogram. Histogram is a type of bar graph that is continuous. Once a histogram is created, we can test the graph for a specific type, a symmetrical data set. If it is true, a normal distribution can be applied along with certain characteristics of the graph. Most important is the area under the normal curve is the probability of the event to occur. Characteristics of a normal distribution include the mean, median, and mode are the same. The graph is symmetric and never touches the bottom axis. Probability is the area under the curve, and we use the Greek letter mu, which is kind of like a weird looking U, to represent the mean or the average. Okay, so what does that mean? Well, it means that in a normal distribution, the data that we're going to look at is symmetrical. Okay, it also means that we're going to use this fancy Greek letter mu, mu, to represent the mean. Okay, why do we do this? Well, we do this to simplify things, and almost any textbook, any statistics textbook is going to use this Greek letter, so that's not unique to our course. So it's important that we recognize that. So far we're just going to look at a type of data set that has some symmetry, certain types of symmetry, and we're going to use this Greek letter mu to represent the mean. Okay, next thing is we're going to talk about the standard deviation. The standard deviation is going to tell us how much the data is spread out. Okay, if we have a very large standard deviation, this means that there is a very large amount of spread throughout the data. An example might be an exam score. So you give your students a midterm exam and there's a very large standard deviation. That means that the student scores are very spread out. If the standard deviation is very small, then the students are very close together. Okay, so let's say you gave a midterm exam and the average grade was a 65, but the standard deviation is only 1 or 2 points. That means that the students on average are only spread out about 1 or 2, so they're very close together. What often occurs is that what I've seen as an instructor, and generally exams are, as funny as it is, often are a normal distribution. The first exam will often be a small standard deviation, and the mean will be somewhere around, I don't know, let's say 80 or 75, right? As time goes on, that standard deviation spreads out. So the more exams I give, the more that standard deviation goes. People drop off the course. People start studying harder. That's when the standard deviation really starts to spread out. So by the time we get to the final exam, usually the standard deviation is a lot. So that's something kind of interesting, and as a student, I know that that would be applicable to you. All right, next we're looking at a histogram for a normal distribution with a mean of 3.8 and a standard deviation of 4.3. So this is just a way of seeing it. You can see that the 3.8 would land somewhere right in that middle there. That is the mean. Standard deviation means that each of the points are varying by 4.3. And so this is kind of what a normal distribution looks like. Okay. With histograms, a little bit of the data kind of seeps out because we're making everything in a rectangle. So we're going to actually work as a perfect curve in this class, and we can do that by making a few assumptions. One of those is going to be the empirical rule. We're going to use the empirical rule, which is the 68, 95, and 99.7 rule. And what it means is we're going to lay the data out in such a way where 34% on either side of the mean there, if you look in the dead center, you see that 34% on each side. That means that 68% of the data is going to lie within one standard deviation from the mean. Okay? This is the empirical rule. It's not perfect, but it sure does make things easier. And when you're first learning this is really the best way to go. So we're going to use this empirical rule a lot for our purposes to get used to these types of ideas: normal distribution, mean, and standard deviation. And we're going to use these probabilities, these percentages, on all of our problems. So for every problem, you can use these same percentages. It doesn't matter what the story is, what the word problem is, you can still use these percentages, okay? Let's look at an example right now. So with an average of 65 and a standard deviation of 5, fill out the curve below. Okay, well, with the average being 65, that means anytime you see the Greek letter mu, we're going to replace it with the number 65. And anytime you see the Greek number sigma, we're going to replace it with the number 5 for this example. And then we can figure out how the data is spreading out. So that's what I've done here. You have 65 in the dead center, and then I'm either going to subtract 5 or add 5 because that's the standard deviation. That's how it's spread out. Then I add 10 or subtract 10 and add 15 or subtract 15. And that tells me how the data is spread out. So once I do that, the values change, and you can see you go 65 in the dead center, and then 60, 70, 55, 75, 50, 80. I fill in my percentages because we're using the empirical rule. And there you go. I filled out the normal distribution curve using this information. Okay. Now, because we've done that, now we can start answering questions about the probability of events occurring. So say this was an exam. What's the probability of the student getting above a 75 on their exam? Okay. Well, above 75, that's going to be the probability or the percentage greater than 75. So that'd be like 2.35 plus 0.15%. We have to add those together. Arrows to show you where that came from. And that would be 2.5%. Okay, so once you have your normal distribution curve filled out, it's very easy to find the probabilities. Very easy. Another example might be an average of 10 minutes, standard deviation of 1.2 minutes. Let's fill out the curve below. So if it's an average of 10 minutes, that means wherever you see the Greek letter mu, that's going to be a 10. And anytime you see the Greek letter sigma, we're going to replace it with 1.2. And that's what I've done here. So you can see I filled it out. Now I'm going to replace it with the actual values that I calculate. And there we are. So I filled that out. Now I'm going to put my percentages in there. And there we are. It's completely filled out. Great. Okay, so what is the chance of having a number that's at least 7.6 minutes? At least 7.6. So 7.6 or greater, right? 7.6 or greater. Well, that means we're going to have to add all the probabilities that are after 7.6. So that's what I've done here. You can see where the numbers come from by the arrows. I'm adding all of the probabilities after 7.6. That gives me 97.5. Okay, but that's not the only way we could do that. Since there's only two probabilities or two percentages that we are not adding, I could do the complement, or I take 100% minus the two that I didn't want to use. If I do that, I will get the exact same answer. This is called using the complement. So I use the complement of what I wanted to find what I do want. So an average of 10 minutes, 1.2 minutes, what is the percent of people that are between 8.8 and 11.2? So what do you think the probability of being between 8.8 and 11.2 is? Well, that would be the 34 plus 34, 68%. Okay, section 15, part 2. This is where we're going to start using z-scores. Well, what is a z-score for? A z-score is going to be a way of calculating these probabilities without the value landing directly on a standard deviation. Okay, so in all the examples we've seen before, and all the examples you see in part 1, all the values will land right on a standard deviation. But what happens if you want to find the probability of something that doesn't land directly on a standard deviation? What would you do then? For that, we're going to use a z-score. So we have a formula to calculate the z-score. Once we find the z-score, we'll look it up in a table, and in the table, we will find that probability. Okay, so the formula is the value minus the mean divided by the standard deviation. So this is the table. I should go back. On page 195 in my textbook, this is where the table is coming from. Okay, it's also on the back of your yellow sheet. You will also see this table on the back of your yellow sheet from conversions, right? So this is the table that I'm referring to. On the left side, you see the z-scores. So I had to break it up for it to fit in a slide. But you see the z-score, and then you see the probability of that z-score occurring. Well, the z-score is telling you how many standard deviations away from the mean you are. So the farthest you could get with our numbers is negative 3.5. That would be 3.5 standard deviations to the left of the mean. Okay, and then the farthest you could go to the right with our numbers is 3.5 to the right. All right. Now, if you notice on this table, if you look at the number 0, we see the probability of 0.5. That's 50%. All that's telling us is that from 0 to the mean, that's 50% of the data. Okay, 50% of the data lies between 0 and the mean. Well, that makes sense because the mean is the average. So that would make sense. Normal distribution, that's true. So that's what it's telling you. Also, hopefully it will make sense after we look at some examples. But the probability is telling you from 0 to that value. Okay? Often we want to find the value to 100. So we'll have to kind of play around with that. But the way that the book has it set up, which is a common way, we're going to have to use our critical thinking skills of what value we actually want to use. But this is the table that you're going to use to find these values. So with an average of 10 minutes and a standard deviation of 1.2 minutes, what is the chance of having a number at least 9 minutes? Okay, well, 9 minutes is going to land between 8.8 and 10. So it doesn't land directly on a standard deviation. So how on earth could we calculate this? Well, we could use a z-score. So if we use the z-score, we can calculate it. I'll replace it with the numbers that I need. 9 being the value that I'm interested in. 10 being the standard deviation, the mean for this. And standard deviation is 1.2. So I find negative 0.83 repeating when I calculate this. So that's my z-score. Now I'm going to look at the table and see what probability corresponds with this. So with our table, the closest I got was negative 0.8, and that's a probability of 21.19%. Okay. Now, this question said at least 9 minutes. What that probability tells me is from 0 to 9 minutes. But I want 9 minutes up because I want at least 9 minutes. At least 9 minutes is greater than or equal to. So I need to subtract this number from 1, the complement, to get the percentage I want. Since it's at least 9 minutes, it has to be greater than. If it said at most, I would have taken the 21.19%. Okay, so that's confusing. We have to keep an eye on that. Okay, let's look at another example. A brand of chocolate comes with an average of 3 grams of sugar with a standard deviation of 0.64 grams. What are the chances you get a piece of chocolate with at most 4 grams of sugar? Okay, well, let's just skip right to the formula. Okay, so I plug in my values. 4 grams of sugar minus the average of 3 grams divided by the standard deviation of grams. I get roughly 1.6 if I round. When I look at my table, I got 94.52%. Now, this says at most, right? At most instead of at least. So I do not need to take the complement of this one. I can just take it as it is, 94.52%. Okay? All right. Well, hopefully that helps. You're going to have a lot of practice with z-scores. You're going to get a lot of practice in, so hopefully that'll at least get you started. Quartiles has to do with cutting data into fourths. Okay, this from an educator's perspective, the thing I see the most with quartiles is standardized test. That's when they really cut people into quartiles or talk about the percentage. So whether or not a student is in the 75th percentile, 25th percentile, that kind of thing. Standardized tests is where I really see it, but it's where you cut data into fourths and kind of look at it. But that's from my real life example. What you go into might be a little different, but the quartile idea is the same. Okay, let's look at an example. So let's just have some random numbers, random integers between 0 and 10. We have these. The first thing to do if you want to cut them into quartiles is to put them in order. Have to put them in order to be able to cut them into fourths. Next, let's do it. We're going to cut them in fourths, so the dead center, and then the other sides. So there we go. Because there is quartile 1, quartile 2, quartile 3. We can plug it in here. Quartile 2 is going to be the dead center. If there is a middle number, we can do this. And so you have quartile 4 and quartile 3. Okay. So hopefully that kind of makes sense. But you have to put it in order. Absolutely have to put it in order. A lot of this can be done in Excel. Okay. A lot of this can just be done plugging in a spreadsheet program. So you can't tell, but this is a live sheet, and I actually did plug this value in. So if you get a list of data, you can just plug it into Excel. You can have Excel. Excel doesn't even have to have an order. It can do it itself, and then it can find the percentile. And the way you do that is you go equal sign, percentile, tell it what values you want, comma, 0.25 for the 25th percentile. Okay. This is saying that for this data, the 25th percentile would be cut off at 3.75. Okay, so close to 4, but in between 3 and 4. Okay. For the 50th percentile, again, we can just plug that into our spreadsheet program and have it calculate it for us. So equal sign, percentile, highlight the data that you want it to calculate this for, comma, 0.5, it cuts the data right in half. Okay, and that would be 5.5. That would be the center for this data. And the 75th percentile, same thing, percentile, the data you want it to calculate, comma, 0.75, and that would be 6.75 for this data. Okay. More examples of that, we can, it's the same thing. You can plug it in your spreadsheet program. You can have it order it for you if you like, and then you can have it do the percentile. So if you're using a spreadsheet program, it's very, very straightforward. Okay, so hopefully that helps, and that should get you started on section 15. I will see you in the next video. Okay, let's look at section 16. Section 16 is all about probability. Last section we were talking about probability within the context of normal distribution. Now we're going to talk about probability just in the classical sense. Okay. So the rules of probability are you take the number of ways an event can occur over the number of possible outcomes. All probabilities will land between 0 and 1. Okay? So you'll never have a negative probability. You'll never have the probability of something occurring that's greater than 100%. Also, the sum of all the probabilities has to equal 100%. We did use that in the last section, that everything has to equal 100%. We're going to continue to use that. We also need to talk about and or in terms of probability. So and in math class is sometimes a little bit different than the way we use it in everyday language. So with math, when you say and, it has to be both or nothing at all. If I want a soda and a bag of chips, then I want both or nothing. Okay? If they didn't have the soda I wanted, I don't want the chips. I don't want anything. So it has to be both of them. With or, also a little bit different than the way we use it in everyday language. So or kind of sounds like it's one or the other. That's usually how we mean it in everyday language. But now in math class, or means one or the other or both or nothing. Okay? We'll get into that with the examples. Conditional probability, we will use if or given, and that will divide the event and change the outcomes. Let's look at the examples. So here we have a chart of students that are passing the class, not passing the class, those that watch the videos, and those that don't. So let's find the probability of a student who watches the videos. Okay, students that watch the videos, there's 95 of them, and there's 135 students for this sample. So that would be roughly 70%. Okay, 70% of the students are watching the videos. Find the probability of a student that watches the videos and passes the class. Okay, if we look at the chart, watches videos and passing class, that's 86 students over the 135 students. So that'd be roughly 64% of them. Find the probability of students that are watching the videos or passing the class. So, or passing the class, that means either one could work or both, right? So, the way I did it, passing the class, there's 101 students passing the class, and then they have to add in the 9 students that are not passing the class but are watching the videos. Divide that by the total. See where those numbers come from. And I got roughly 82%. 82% students are watching the videos or passing the class, or both. Find the probability of someone passing if they did not watch the videos. So passing but not watching the videos. So that would be 40 students that are not watching the videos, and there's 15 that are passing. Okay. Let's look at a different chart. So this has to do with generations, ages of people, and social media platforms: Facebook, Instagram, Snapchat, Twitter, and TikTok. and how those demographics break down. Calculate the probability of selecting one person that uses Instagram. So that would be an Instagram user over the total. So you can see where those numbers come from. And for this data set, that would be roughly 23%. Okay, roughly 23% are Instagram users out of this data set. Okay, find the probability of selecting a random person who uses Snapchat and is from Generation Z. Okay, both have to apply, Snapchat users and Generation Z. Well, that would be 668 over the total. And so that would roughly be 9%. 9% are from Generation Z and use Snapchat. What about someone who uses TikTok or Twitter? Or means we have to add them together because either can apply. We can divide by the total. And so that would be, well, roughly 27%. If selecting from only Facebook users, what is the probability a person is a baby boomer? So we're only going to look at Facebook users. We're not going to look at anyone else. And then we're going to talk about baby boomers. So this is going to be 289 baby boomers that used Facebook over the total number of Facebook users. Oops, I went over that too fast. And that would be roughly 12%. What are the chances of someone being from Generation X or Generation Z? Well, we could just add those groups together and then divide by the total. So that would give us roughly 56% are from those two generations. Calculate the probability of selecting one person who is a millennial and uses Facebook. Okay, well, we want both groups. So we have 823 millennials who used Facebook over the total. And that would be roughly 11%. What is the probability of finding a Snapchat user given that they are from Generation X? So we're only going to consider Generation X for this problem. We have 120 from Generation X that use Snapchat. And we have 1,476 Generation X participants in the data set. And that's going to be roughly 8%. What is the probability of someone who is a millennial or TikTok user? So we have to add both of those, but not overcount. The way I chose to do this was to demonstrate that you can subtract. So you have millennials there. Then you have your TikTok users, and then I'll just subtract the overlapping intersection. So roughly 41%. Given all the TikTok users, what are the chances of someone being in Generation Z? Okay. So I have 601 Generation Z TikTok users divided by total TikTok users of the data set. 77.2%. So this is considerably likely that if they are a TikTok user, they are from Generation Z. All right. Section 16, that should say section 16, part 2. This is going to be the false positive, false negative part of the course, and it's really just best to look at an example. So we have a test here. You can think of like a COVID test or a pregnancy test. These are probably the two most common tests of our age, and they have a particular accuracy rate. This test that we're going to look up for the example is 85% accurate. And it's going to be, we're going to test 1,000 people. 20% of these people actually have the disease, and we're going to fill out this chart, okay? So we can fill out, if we know 20% have it, we can fill out 20% have the disease, 80% do not have the disease, and then we can determine how many people should test positive, should test negative. So first, I fill out the rightmost column, 20% of 1,000, 80% of 1,000. The problem tells me 20% have the disease. Well, that leaves 80% of the rest, right? Because 80 and 20 is 100. So that'd be 200 and 800. Okay, now I can start filling out the positive, testing negative. So for the top row there, the majority should test positive because these people actually have the disease. Well, the test is only 85% accurate. So 85% of the 200 will go with the positive and 15% will go with the negative. Okay, we'll do the same for does not have the disease, but the other way around. Okay, so 15% of the 800 will go with testing positive since these people don't actually have the disease. 85% will go with the 800. And then for the totals, we can just add them. Okay. All right. Now we can answer some questions. If a person gets a positive test, what are the chances they don't have the disease? So this person tested positive, but what is the chance they don't actually have the disease? So we're only going to consider those that tested positive. 120 people do not have the disease and tested positive. Over 290 that tested positive. Roughly 41%. This would be a false positive. They do not have it. They tested positive. False meaning incorrect. Positive meaning they tested positive for the disease. What is the probability that a person has the disease if they get a negative result? So if they got a negative result, we're only going to consider those that tested negative, and we're going to only consider those that have the disease. So about 4%. This should always be, for any test, this should always be the smallest percentage. And this would be a false negative. Okay? False meaning not true, incorrect. Negative meaning they tested negative for the disease, but they actually have it. And for any test, this should be the smallest group. Okay? Given a person has a negative result, what's the probability they don't have the disease? Okay, we're only going to consider those that are negative, and we're only going to look at those that don't have the disease. So we got 680, about 96%. This would be a true negative. Okay, true negative. What is the probability of having the disease and getting a positive result? Okay, so 170 people actually have the disease and tested positive. Over the total, 17%. Let's look at another example. Test measures for pregnancy with a 99% accuracy. In the survey, 250 women took the test, but only 185 were actually pregnant. Okay, they give it to us in numbers, so I can determine what the right-hand column should be. Now the test is 99% accurate, so I can easily determine what the first row should be. 99 should test positive, 1% should test negative. The converse would be true for this. 1% should test positive if they're not actually pregnant, and 99 should test negative if they're not actually pregnant. Okay, what are the chances that a woman was pregnant given they had a positive result? So we take the 183 over the 183.8. It's pretty close. Almost 100% there. All right, another example. Out of 32,000 people, 25% actually speed on the road. A test with 95% accuracy can test if this is true. So I can fill out the first column there. 25%, 75%. This is the way I always start these problems, by the way. Then we do the accuracy of the test. Accuracy of the test. And then we can do the totals. And now we can answer questions. What is the probability of catching someone speeding given they have a negative result? Okay, they have a negative result. They are actually speeding. So 1.7. Okay. Hopefully that helps. Hopefully that at least gets you started anyway. What's due? Project 2 is due Sunday. Everything else is due Wednesday. Please get a hold of me if you have any questions. Next time, final exam review. We're going to get ready. We're also going to talk about section 17, which is really short, so it shouldn't be any trouble. That is the end, and I hope you have a good weekend, and please let me know if you have any further questions. Talk to you next time.